I want those of us that are already in class to at least begin a chat before the others join us. Now, I'm going to ask a question. Please be fast. Answer me. When did you learn? When did you first learn about calculus, especially the idea of differentiation? At what SS2? Good, good, good. Vectors. When did you first hear about something called vectors? Good. Okay, today we are dealing with tensor analysis 1. We have tensor analysis 2, and we probably have 3. And we are essentially looking at the differential and integral calculus with tensors. I want to draw your attention to a fact that you already know differential and integral calculus with scalars. You've been, since secondary school, you've been looking at a curve of y is equal to function of x. And then you'll be taking limits on that, on the x-axis. You've been doing derivatives, you've been doing integrals. You've done a lot of things. And in fact, when you were sitting for your JAMB, for your SSCE exam, all they were asking you were around the differential and integral calculus with scalars. Now, when you try to deal with vectors and tensors, things become a lot more complicated. But the fundamental idea is the same. In order for you to move from scalars to tensors and vectors with your differential as well as your integral calculus, you will need to go back to the fundamental definitions of limits, of differentiation, what those things really mean. To be sure, let me tell you, you know that if I ask you to differentiate y is equal to x raised to power 4, okay, let us do that. Tell me the answer in the, what is y is equal to x to power 4? Differentiate y is equal to x to power 4. Tell me the answer in the chat room. Y is equal to x to power 4. Okay, you have been so traumatized with this thing. You all know it, because if you don't know it, you won't pass your JAMB, you won't pass your SSCE, you won't pass. Now, I have a bad news for you. Let me give you a bad news. Now, let me first of all get my screen back on. The bad news is that is really not the differentiation. That one you know, that one that has been thoroughly examined, is not the real issue. The real issue is the first principles, the first thing you are taught, how the derivative is the limit of a quotient. That one is very laborious. And as soon as you knew the formula, you forgot about it. We are going to go back to not how you got that your answer now is 4x to power 3, but if you were to do it from first principles, the definition of differentiation, that is what matters. The fact that you are able, like a robot, to regurgitate it, you know that the derivative of sin x is cos x, you know that the derivative of e to power x is e to power x, you know so many things. All those things are consequences based on the fundamental definition of derivative. For us to move our act a little bit further, we will need to go back to that fundamental definition. And you will see now how the one you've been avoiding, those fundamental definitions are far more important than the one that excites you. That's the bad news. The good news is that it is not harder fundamentally than what you've already done. It may look so, but my job is to make sure, is to assure you and to make sure you know, you can see. It can be demonstrated to you that if you could understand the previous one, you can understand this one also. 2, if you think the previous one was useful, what you are going to learn now is far more useful than the previous thing. In fact, the previous differentiation and integral calculus with scalars is to prepare you for what we are going to learn today. That's all that it is really meant for. You will see the reason why this is more important than that. Let us begin with a very simple example of a brake disk, of a brake subsystem. What you are seeing on the screen is 1/4 of the brake disk of the brake subassembly, just 1/4 of it. On the other side of it that you cannot see, that's the part where it meshes with the brake disc itself. When you match your brake, the thing clamps together and try to stop a rotating disc, and it will generate enormous temperatures. In fact, if you put your hand there, it will burn it. If you put water there to boil it, it can really turn red hot because it is very, very hot. Now, there are forces that are exerted on it. Forces are exerted on it, so it generates stresses and strains. Even the temperature also creates stresses and strains, because when something gets hot, it becomes elongated, and if you prevent it from elongating, it creates stresses. So the stresses are coming from two fundamental principles. It's coming from the principle of heat. It's also coming from the principle of stress. Both of them are working together to create the situation. Now, why am I looking at 1/4 of the system? Why am I not looking at the whole thing? It is not necessary to look at the whole thing, because what is happening in this 1/4 by two planes of symmetry is repeated. If I can study what is happening here, it's just the same. If I add two planes of symmetry to it, it will give me the full circle, and I have the whole thing. But there is no change. Everything is symmetrical. So that's why we are looking at it in this particular point of view. Only 1/4 of it. Now, what does it take to properly design a brake subsystem? What would you have done to say you have properly designed a brake subsystem? What you would have done is that you would have specified the geometry of it. You would have specified the materials you used in terms of their sizes and quantities and properties, so that all of this together will give us an optimal brake in terms of production and economy. When you do all of that, you have designed and probably also manufactured a brake or a brake subsystem. Now, let us look at the physical quantities that are involved. What physical quantities are involved in this thing? Let us go to the chat room. I want you to tell me what physical quantities you think are involved in the brake. Just list as many of them as you can think about. What physical quantities do we have to consider when we are looking at the brake or a brake system or a brake subassembly? What physical quantities? What physical quantities matter? Mass? Okay. Okay, do you think temperature matters? Do you think temperature matters? Do you think temperature matters? I'm asking. Okay, you think temperature matters? Okay. What about strain? What about stress? What about rotational velocity? List for me what else you think matters. Okay, density of the material. Friction. Okay. Okay, heat capacity. Good. So you can see all the things that matter. Okay, let us now go back. I want to pressure. Okay, because the pressure, that is, pressure is just a type of stress. That's why I don't want to talk of pressure, because pressure is just stress. It's just it's just one particular kind of stress. Yeah. Breaking force. Okay, so you know the things that matter. So I want to go back to the slides and continue discussing from that point of view. Okay, so among several things that we will look at will be temperature, stress, displacement, strain fields in the analysis of the optimal design of a brake rotor. And we will solve the governing equations. What are governing equations? What do you think governing equations are? We solve governing equations. What are governing equations? I'm back again in the chat room. What are governing equations? What are governing equations? Well, Patrick, you are not wrong, but that's not what I want to hear. Well, that describe the state. True, but that's not what I want. Principles that describe a parameter. You are not wrong, David, but I still want something else. What are governing equations? You are all tired. Okay, make two more efforts. Abdulazim Shobie. I seen your answer, but I am not. I still want something more. One more, just one more effort. I will tell you what governing equations that describe. Well, Moyo Fade is the closest to what I'm looking for. Is there are equations that relate these things that we think matter, that relate those things together. Fundamental mathematics that describe how the body behaves. Well, yes, but what your father said is closer to what I am looking for. They tell us what relationships must exist between the stresses, the strains, the velocity, all those things that matter, all those variables that we think are important. The governing equations relate them together. Relate them together. I think nobody has done better than Moyofade so far. So that's the thing. So that's what the governing equations. Now the next question: how do we arrive at governing equations? Where do they come from? Where do they come from? How do we get those governing equations? You have done some governing equations by this time. How do we get them? Okay. Governing equations don't come, well, they don't all come from, some of them come from experimental data, I will tell you, but that's not fundamentally where they come from. Okay, so I want to answer those questions now. Just I want to answer them because I didn't have them in the slides. I didn't plan to go this route. First of all, governing equations. Governing equations relate the quantities that arise in the changes that we see in the subsystems, like stresses, temperatures, strains, displacement. They relate those things. Where do they come from? So the equations that come from balance, from natural laws, the laws of nature, that are also called balance laws, are about balance of mass. You cannot create or destroy mass unless you are in relativistic mode where you are converting the mass to energy. But ordinarily, with regular speeds on Earth, you will not create mass, you will not destroy mass. So the mass must be conserved, the momentum must be conserved, energy must be conserved, and there are entropy laws that shows that entropy must increase if the system is isolated, and some other things. Now, the experiment, the second thing, experimental sources. The Okay. So there are two sources of the governing equations. Source one is the balance laws. You subject the thing to all the balance laws of nature. You look at the fact that mass must balance, momentum must balance using Newton's second law. And then you look at the conservation of energy, that the energy must balance, the entropy laws. And then you also look at material behavior. Material behavior, you have to find that experimentally. For instance, if you put rubber in the same stress situation as you put iron, the bending and the stress and the strain you will get will be different. So you want to know that for every material you use. It is when you put all of these things together that you have the governing equations. And it is those governing equations you solve. Now, so that is what engineering design is all about, solving those equations. Those equations are far more complicated than the equations you have in your elementary calculus. The y is equal to function of x that you will get is far more complicated. It is not relating one scalar to another scalar. It's relating a vector to tensor or to many other kinds of things that they will, and the boundary conditions are really very complicated, and they are not going to be solved as easily as the equations you use to pass your JAMB and the equations you use to pass your SSCE. Those equations are trivial when it comes to real analysis. When it comes to real analysis, you cannot even solve these equations with the plenty of mathematics. You have to go to numeric analysis. And when you get to numeric analysis, you have to change your derivative definition to numerical definition. And you are going to be using the same fundamental laws, fundamental definitions, rather than those crap things you have been doing. We are going to go back to the fundamental definition of differentiation. We're going to go back to the fundamental definition of integral. We're going to go back to them and create solution methods. And those solution methods are called numerical methods. They usually use finite element analysis. Your tools that you use to draw, like Fusion 360, like Autodesk Inventor, like AutoCAD, they already have all these equations programmed in them so that you can use them for your analysis. Now, that leads us to what we are going to study today. What are we studying today? What we are studying today is rooted in a very simple fact that the things that you are relating, temperature, is temperature stress or strain? Is temperature, is it a scalar or vector or tensor? Temperature, stress, displacement, strain field. Again, go back to the chat room. Tell me what temperature is, what stress is, what displacement is, and what strain is. Just tell me what these things are. Before, temperature, stress, displacement, and strain. Go and tell me what they are. Are they scalar? Are they vector? Are they tensor? Let's go back to the chat room. I want you to tell me what these things are. Okay. Okay. Somebody says stress is a scalar. Somebody says stress is a vector, tensor vector. Stress vector, displacement, strain vector. Okay. What about strain? Itunu. Chibuzo, you forgot strain. Abdul Razak, you forgot some things. Just tell me what you think they are. Okay. What is moment of inertia? Is it a scalar? Is it a vector? Or is it a tensor? What's the moment of inertia? Is it a scalar? Is it a... What's temperature gradient? What about Victoria? What about velocity gradient? What about velocity gradient? Okay, good. Similarly, okay, so unlike surprise, let me give you some more surprises. Even though temperature itself is a scalar, temperature gradient is a vector. Velocity is a vector. Velocity gradient is a tensor. Let me see which ones you got very wrongly, so that I can talk about that. Moment of inertia is a tensor. Temperature is a scalar. Stress is a tensor. Displacement is a vector. Strain is a tensor. Strain has 9 components. Okay. Yes. Where I'm getting at is this. There are two things before I change from this picture. I just thought about this picture in the last few minutes before the class started, because some people are asking me, why are we doing all these things? Okay, let me actually show you why we are doing them. First of all, those governing equations, they relate. Next week, I will bring some of those governing equations for you to see. I will do that next week. Some of those governing equations, they relate velocity gradient, temperature gradient, stress, strain, and so on. And they are defined not on the x-axis, they are defined in x, y, and z axis. They are defined everywhere. They are defined, for instance, in your brake disc. You can go in the x direction, you can go in the y direction, you can go in the z direction, and you will always find changes. And so they are not functions of a single variable like the ones you've been using in your jump and in your SSCE. They are far more complicated than that. They are defined in the Euclidean point space. They are not defined on the x-axis or on the y-axis or on the z-axis. They are defined everywhere. And they are relating these tensors to each other. So the differentiation you need is not just differentiation along x-axis. You are looking for gradient that takes differentiation along x, y, and z-axis at once. That's one thing. You may also need to differentiate with respect to a vector. For instance, the strain energy density is a scalar quantity. If you want to get strains from them, you have to differentiate the strain energy density with respect to the stress. So you are differentiating a scalar with respect to a tensor. Those are things you have never considered. In fact, let me give you something that you have seen, but you never even thought about doing. Suppose I told you to differentiate. Suppose I told you, you can take a pencil and write this down. And it's something you should have thought about, but somehow you didn't think about it. Suppose you were to differentiate the magnitude of a vector. You know how to get the magnitude of a vector. Suppose I give you the magnitude of a vector and say, get me the differentiation of that with respect to the vector itself. Suppose I told you to differentiate the magnitude of a vector with respect to the vector itself. Does that look like a reasonable thing to do? You cannot do that thing with your current methods. Let me see where I wrote it down. Let me see whether I wrote it somewhere here. No, it is in the next. This is the next slide. I just want to show you that thing, what it looks like, so that you will understand why we are doing what we are doing. I thought I wrote it. Let me just see. Yes. What I'm saying here is that suppose I want you to arrive at this result. You see, you are differentiating the magnitude of vector V with respect to V itself. This is something completely beyond the power of the calculus you have done, because you have just been doing the calculus of scalars. You have not really done. I will show you. You thought you have done. You thought you have differentiated vectors, but every time somebody is introducing differentiation to you, I will show you how they limit it without telling you, and you just never left where that limit is set. We are going to remove all those limits, and we can differentiate anything with respect to anything. And for us to do that, we need new knowledge, and it is that new knowledge I'm bringing to you from today and 2 more weeks of it. So we will look at those things. This is, for instance, this is not for this week. We will look at this next week, where we are differentiating the magnitude of the vector V, which is a scalar, with respect to vector V itself. The answer is V over this, but the logic to get this is not at the level of all the, even if you got 400 over 400 in JAMB, you will not be able to do this because of that. This is far beyond what they are talking about at that level. And why do we need this? We need this because the quantities you need in design are not scalars. They are vectors and tensors. And those are the things that we need to do the calculus of. So we are now going to be doing the calculus, the differential and the integral calculus of scalars, of vectors, and of tensors. We are going to move away from just doing the differential and integral calculus of scalars that you have been doing, and we're going to move to that of scalars, vectors, and tensors. And that is going to begin from today. So we have spent time, but I think that time is well spent, because you need to understand where we are going. Because when you don't know where we are going, you start wondering, why is this man carrying us through all of these things? If you do not do that, you will not be able to do this analysis. You will be able to do it. And in fact, last thing I want to say about this slide. When you do your simulation in your software, it will give you results. For instance, since the stress has 9 components, where it is giving you the stress field, how is it going to tell you about all the 9 components? The answer is that it will not tell you about the 9 components. It's going to take one of the principal invariants of that tensor and it will tell you about that. And that will be enough because that is characteristic enough of what is going on. Instead of running after 9 rats, you are going to be running after only one. And if you don't, you will see it there. If anybody who has done a simulation with Fusion 360 or with Inventor will know that eventually they tell you about the von Mises stress. The von Mises stress is one of those principal invariants we are talking about. So instead of your running, you cannot be running after the 9 stresses. You have to run after a characteristic value. And that is why we do not deal with the tensors directly. We deal with the principal invariants, things that are related, or the eigenvalues, or the characteristics of it. Here, you have the displacement field. The displacement is a vector. There are 3 displacements. So you are likely to be looking at the magnitude of the displacement field. So instead of looking at displacement in X, displacement in Y, displacement in Z, you are looking at the magnitude of the displacement. So instead of 3 things, when you are dealing with a vector, you want to deal with that one thing, which is the magnitude. And the temperature field is a scalar. That one is easy because it's a scalar. You might just look at the temperature field itself. Here, you might look at this factor of safety field. All these things are no longer the kind of things you are looking at. But when it comes to realistic design, the equations you are used to, the equations that are very nice for you, that you used to beat all your mates, that they told you that you are very brilliant because you knew math, physics, all those things are quite elementary. We are going to go into something more realistic from now on. So let us move on now. The scope of the lecture. The issues which are covered in today's lecture are not hard to understand. They are fundamental to all tensor analysis. Be careful to note any area of difficulty. If you are specific, I can assist you. We are going to introduce the Gateau differential as the solution to our inability to divide by tensors or vectors when we want to define a derivative. I will get to that. Because the question is, how do you differentiate with respect to a large object when neither of these spaces allow division? You know, you can do 4 kinds of products with vectors. Multiplication with a scalar product, a vector product, and a tensor product. But there is no division allowed. You are not allowed to divide for vectors. You are not allowed to divide for tensors. So every definition of differentiation involves a division, and we are not allowed to divide with respect to a vector or tensor. How then do we define differentiation with respect to a vector or a tensor? We shall answer that question today. Did you know that multiplication is really an addition that we create a smart formula to do? Okay, I don't want to talk about that. Forget that we are in a serious course. Let us say we are trying to make a bet. If I win, I get your phone. If you win, you get mine. Here is the bet. I am proposing that the reason why you memorize in calculus is that you don't know the underlying algebra or the fundamental concept it is based on. If you crammed elementary calculus, you are hopelessly cramming in advanced calculus because there are so many things to cram. If I explain the fundamental issue of calculus, give you the insight, you will never really need to cram because you understand what is really going on. I'm willing to bet, but you are not close enough, and I don't know whether I like your phone enough to go to a bet with you. So the first thing I'm going to do after I've just given you an explanation, I'm taking you back to the beginning of your calculus, which you just imagine you are in SS1. And we want to say, okay, what is a limit? What is a limit? See the colored arrow that I have below. I will tell you that give x naught and w naught. Let us say they are all real numbers. we can say that the limit of a scalar valued function, let us say there's a function defined at every point. That is, at point X, you have a value for the function. It could be the temperature. It could be the velocity. So let us even not talk of velocity. Let us talk of scalars. It could be the temperature. It could be the color. It could be something that changes from point to point. Here, you can see color changes. It could be the color. It could be a code for each color that you are seeing there. So at every point along the x-axis, there's a definition of that function. If I tell you that the limit as x tends to x naught, as we're approaching x naught, of that particular function is w naught, what do I mean? What do I even mean by limit? What do I mean by limit? Very simple. And once you understand that, you will see that everything else becomes easy. When I talk of limit, I am not interested in going to find a value at x naught. I'm not interested. Why will I not be interested? Maybe there are crocodiles and snakes there that will bite me, and I cannot reach x naught. But I can get as close as I like, except that I am not able to reach x naught. So I want to tell myself what is happening at x naught without necessarily getting there. That is what we mean by limit. I want to check what is happening. What is it that is happening at x naught? I am allowed to be as close as I like, but I am not allowed to go there directly. And I want to find what the value or the function will be at x naught, given that I know every other thing about the function. I know the value at all the points around it, except that I may not necessarily know the value at x naught. This is the textbook definition. And that textbook definition is loaded. Loaded. I will read it for you, and I will spend time to just explain what it really is saying. And you will see that what it's saying is very simple, but it's very precise. If for any pre-assigned real number epsilon greater than 0, no matter how small, we can always find a real number delta greater than 0, such that the difference between the value of the function and w0 can be made smaller than epsilon, no matter how small epsilon is. Whenever we are in a neighborhood, a delta neighborhood of the point, that function is said to be continuous at x naught if f of x naught exists and f of x naught is equal to w naught. So the limit is w0 if we can make the difference between the value and the function that is close to be smaller than any number we like. So we can make it arbitrarily small. We don't need to get there. We have the value w naught, and we say that if there is this value w naught that exists, and we can always make the value of the function so small, smaller than any number you can choose. So let us say somebody chooses 0.1. Another person says, no, that's too big. I want to choose 0.01. We can make the difference smaller than 0.01. Somebody else comes and says, I want 0.001. Okay, we can still make it by shrinking the distance, we can make it less. Another person comes, I want it to be less than 0.00000000001. Then no problem. All I need to do is to make my delta smaller. I will still make sure that the difference is smaller. If I can always do that, then I say the limit at that point x naught is that w naught. If I can't do that, if somebody can suggest a number that is so small that you can't do that, then that thing doesn't have a limit of w naught at that point. That is what it's saying. In less fanciful words, we are simply saying that we can find a neighborhood where the absolute value of the difference between f of x, and w naught can be made as small as we choose a priori. We make that choice a priori, and we now try to find the delta that will make it happen. If we can do that always, then we say the limit as x tends to x naught of f of x is equal to w naught. If it is not possible, then that is not the limit, or maybe the limit does not even exist. There are functions that have no limit at a particular point. For instance, you know that tangent, for instance, doesn't have a limit at, I think, is it not around 90 degrees? It doesn't have a limit. Before 90, it's going to plus infinity. After 90, it's going to minus infinity. There's no limit at that point. So such things exist that they don't have They don't have limit. So it's not every function. There are functions that are well behaved, and there are functions that are not well behaved. It turns out that when we get to advanced calculus, we do not make a lot of assumptions. In fact, we may not be able to do things in closed form. We may have to use numerical analysis to get our results. So I decided to continue expanding the thing. If I continue expanding the same line, you will see that I can know the color at x naught, but simply if I keep expanding this line, is without changing delta. It's the same thing as not expanding the line and making delta small. You can look at it that a time will come when I expand the line enough that there will be no difference in the color inside that delta. So I know that that is the color at the point I'm looking for, because it is the same thing everywhere. So we may be unable to get to the point, but whatever the purity of color we may desire in the range, we can keep reducing the size or keep increasing the length of the x-axis until we achieve it, no matter how pure the color specification we set at the beginning. That is, so it doesn't have to be a number. It can be a color, it can be a weight, it can be a temperature, it can be anything. And we can find a limit. So the first thing you do is that you understand the idea of what limit is. I've used Mathematica. Those of you who have access to Mathematica, you can do this. Let us say I'm interested in the limit as x tends to 1 of sine of x minus 1 over x minus 1, which turns out to be the same thing as limit as x tends to 0 of sine of x over x. That limit is equal to 1. Look at this graph that I have here. If I plot x minus 1 at x tends to 1, it is 0. If I plot sine x minus 1 at x tends to 1, it is 0. So if I try to merely substitute the value at 1, I'm going to get 0 over 0, which is not a number. It's a nan. Nan, not the infant formula, but this is an error that what you are looking at is not a number. So you are not allowed at this point to just simply substitute, because if you substitute, you get 0 up, 0 down. You know, our mathematics does not define 0 up, 0 down. You cannot divide by 0. So you have done something wrong. But if instead of that, if we agree that the value of what we are looking at is at this point that we have rubbed out, that's the point x is equal to 1. That's where we are looking for it. So we are imagining we can't reach that point, but we can get close to it. We can start from 0, 0.4. If we are 0.4, sine of x minus 1 is 0.56, so on. And x minus 1 itself is 0.6. And the quotient is 0.94. When we get to 0.95, we have the 2. The quotient is 0.999. When we get to 0.999, the quotient is now 0.999999. By the time we get to 0.9999, the division of the 2 is 0.9. You can see. So you can see as we are going that we are actually going to a limit. It is not that we are not making it up. We are going to a limit. Suppose you started from the other side. Suppose you started from 1.05 and you begin to reduce it to 1.01, 1.001, 1.00001. You can see again you are approaching something. And if you continue doing it, it is clear to everybody that is fair that this thing is approaching the value of 1. That is what it's approaching. Whether you are coming from the left, or you are coming from up or down, from left or right, you are approaching 1. That is what we mean by limit. If you cannot perform this exercise correctly, that you can achieve, you can see what the limit is by just looking at what the number is tending to. For instance, it started going up here, and then when it almost reached 1, it started coming down. So it is diverging away from it. And if you look at the graph, you can see that as you're approaching 1, it is going up, it gets to a point, it maximizes, and then it starts going down. That is what it is. This is a classical example of what we mean by limit. If in addition to finding the limit, We now find that we can actually substitute the number there and it gives us the same value. Then we say the thing is continuous. In this case, you can't do it, but you can use L'Hopital's rule and differentiate up and down, and that one can still give you the correct answer in that case. But let us, at least this is a classical example of, if they taught you limit like this in secondary school, I don't think you will forget it, because you want to run away from it, because it looks like a confusing idea. In my own situation, my teacher did not appear to understand it well enough. I don't want to say bad things about an old man who is even be dead by now. But I think if you understand it like this, if you can do this spreadsheet for anything, this is how to really settle the matter of limit with ease. I've kept you for about 1 hour. It is my tradition to give you a rest of 10 minutes this time. So we will come back at 11:15. If you have comments on what we have done so far, because we are now going to take off. I've given you enough background. I will go now to the real meat of today's class when you come back. I will stay on the chat. So anybody who wants to chat with me can continue during the break. Thank you. So if you have a question or comments, we can discuss that. If not, I will turn off my microphone so that I can go and do other things while I also take a break. Okay, nobody. Okay, welcome back, everybody. So let us go back to the slides. Okay, so let us remind ourselves, what do we mean by scalar value functions of scalar arguments? So what we mean is that the argument here is x, is scalar, and the function is y, is also scalar. Here again, the argument is x, is a scalar. The function itself is also a scalar. Here, the argument is a scalar. The function is 1 over root x, which is also a scalar. So these are scalar valued functions of scalar arguments. It is possible to have vector valued functions of scalar arguments. It's possible to have scalar value functions of vector argument. We will see all the possible combinations. So the function can be one type and the argument can be another type. And the way you treat them will be dependent on the kind of combination you have. Right now, from our JAMB to our SSCE to our 100 level, 200 level, now at 300 level, we have mostly dealt with scalar valued functions of scalar arguments. We have even dealt with vector valued functions of scalar arguments. I will show you those ones. But we have never dealt with vector valued functions of vector arguments. We have never done that. The math we are going to learn now will allow us to deal with vector valued functions of vector arguments and scalar valued functions of vector arguments and so many other things that used to be beyond our ability until now. What if memorization are not allowed? Can you find these derivatives? Of course, you know that the derivative of the first one is 2x, the second one is cos x, and the third one is 1 over minus half of x to power minus 3 over 2. That is what it is, because we know we have some formula. But suppose I asked you to find all these things by first principles, that you don't have any of those formulas, you'll see that they're a little bit more difficult. But it is those first principles that we will now rely on, because they are powerful enough to carry us through anything we want to do. This memorization, they will die at scalar value functions of scalar arguments. You can't go beyond that. Fundamental principles is that's how you proceed. It turns out that memorization can help you pass only general principles, advanced knowledge. Only the general principles, advanced knowledge. You have memorized long to get this far. It does not last forever. Here, there is the end of that ability. It's not that ability you will need to move from this point on. Here is a vector valued function of scalar argument. Here, the function itself is a vector, but the argument is a scalar. The argument here is t. How do you proceed to differentiate this? What does it mean? How will you proceed? Whether vector or tensor, differentiating a large object like a vector or tensor with a scalar argument is not different from what you have been doing. If the argument remains scalar, you can still do it, even with your old knowledge. There are two ways to look at this. You can turn it to three equations. You can turn it to three scalar functions in scalar arguments. So you just do three. Or you can do it as a single one. It is still the same. It's still the same thing, because if you want to divide by anything, it's t you will divide by, as because t is a scalar, you can get away with it. This is not a problem. You can do this one, and you've been doing this. So your knowledge left you at vector valued functions of scalars, but it did not reach functions of vectors, whether it's vector valued or scalar valued. You cannot, your math cannot take you to scalar valued function of vector argument. You can't do that right now. Scalar value functions of vector and tensor arguments. Are there examples? Oh yes. Oh yes. Oh yes, there are examples. Let us start. If the magnitude of a vector is a scalar, you know that. It is a scalar valued function of a vector argument. The argument is a vector, but the value produced is a scalar. So this is one example of something that your math cannot differentiate. The three principal invariants of tensors are they are all scalars, but they have vector argument. I1 of t, I2 of t, I3 of t. All of them are scalar value functions of tensor arguments. You can't differentiate this with your present knowledge. Can we differentiate this with the arguments? Not with the knowledge we have so far. We need new knowledge to be able to do ddv of v, ddt of I3, ddt of determinant, etc. We cannot do them by the methods we know right now. Are there tensor valued functions of tensor argument? Plenty. Now, because in the previous page, we saw scalar valued functions of vectors and tensors. Are there vector valued or tensor valued functions of vector and tensor argument? There are. For example, the cofactor of a tensor is a tensor itself, and it is a tensor function of tensors. It has in its argument the tensor and its determinant to compute the cofactor. So if you try to differentiate the cofactor, you are differentiating a tensor valued function of a tensor argument. And like I said, today we have seen that stress is a tensor, so it has a cofactor. Strain is a tensor, it has a cofactor. The moment of inertia is a tensor, so it has a cofactor. What else? The velocity gradient is a tensor, so it has a. In fact, the gradient of any vector is a tensor. So it does not only velocity. Any vector you know, the gradient of it is a tensor. That is why, for those of you who have done gradient, divergence, and curl, your teacher would have been very careful that you never take the gradient of a vector. You only took the gradient of a scalar, because if you took the gradient of a vector, you are going to get something he knows you don't know anything about. So he doesn't want to introduce it. So you think it's only scalars that you can take their gradient. You can take gradient of everything. It's just that the order of that quantity rises by 1 when you take its gradient. So differentiating this defies all the math you know so far. The differentiation of a scalar value function of a vector or tensor argument is already problematic. You have been limited to functions that have scalar arguments so far. We begin to consolidate that before introducing new things. You master that first. So this is how you differentiate from first principles. You want to differentiate y is equal to x squared for first principles. You say, okay, let it increase by h. You are taking the limit as h tends to 0 of the difference divided by h. And because the function is x squared, so if it increases by h, so it is x plus h squared minus x squared. Open the bracket, you have it is x squared plus 2xh plus h squared minus x squared. If you subtract, you have it is limit as h tends to 0 of 2xh over plus h squared over h. If you divide, it is 2xh over h, which does not have any h again, so you can take it out. And then what is remaining is h squared over h, which is limit as h tends to 0 of h, which vanishes, and that's how you got 2x. Of course, this is a much longer process than just say 2x straight away because you have cracked the formula. But I told you, the difference here is that whereas this one is very slow to get this answer, but it will always get the answer. It doesn't matter which function you are dealing with. This method will always get the answer. Your own, that is very fast, we get some cheap answers, and when it going becomes tough, it doesn't have any answer. So that's it. That's the reason why we are going to stick with the first principles. Doesn't matter whether it is sin x, you go through the same process, first principles, you get the answer. So if it is cos h minus 1 over h, again, you can use a spreadsheet and do what we did before, and you'll see that the answer in this case is 0, because it just goes linearly to 0 if you take the limit. So let us now talk of differentiation of large objects. We're already familiar with the techniques of differentiation of scalar value functions with respect to scalar arguments. These objects are defined in scalar domains. That is, the arguments they have are scalars. The derivative of the function is this. Pose no problems, as the divisions by scalars is well defined. We can always divide by a scalar. As long as the argument of the function is a scalar, there's no problem of division because you can divide by a scalar. Things become more complex when we handle tensors. A second order tensor contains 9 scalars. A vector is a first order tensor, contains 3 scalar members. Complication does not arise from the size of the object themselves. Derivation of tensor objects with respect to scalar domains with some adjustment basically conforms to the same rules as the above derivation of scalars. As long as the domain is a scalar domain, no problem. Division by a tensor of a tensor by a scalar is accomplished by multiplying the tensor by the inverse of the scalar. So if you want to divide a tensor by a scalar, no problem. Just get the inverse of the scalar and use it as a scalar multiple of the tensor, which is defined. This operation is defined in all vector spaces. It's also defined in tensor space because, seriously speaking, a tensor space is really a different type of vector space. So consequently, if we have a tensor which varies with respect to t, like time, we can differentiate it with respect to t and form this quotient, limit as h tends to 0, t evaluated at t plus h minus t evaluated at t divided by h, which is written as 1 over h times that. The product of the scalar and the difference of the tensors are defined. They are defined, and the tensors, they are also tensors. So the product of, just like the product of a scalar with a vector is a vector, the product of a scalar with a tensor is a tensor. Hence, the derivative of a vector or a tensor with respect to a scalar is a vector or a tensor, depending on what the function itself originally was. So we can go through first principles and differentiate the product of alpha t, where alpha is a constant, where alpha and t are both functions of t. If we do that, we can see that at the end of the day, if you follow this equality, which I will not go into, which I will let you do on your own, you will see that at the end, it follows the chain rule, even though the objects are not of the same type. This is a scalar, this is a tensor. You see, it is alpha dt plus the alpha dt. The only thing is that the order must always be preserved. Maybe not here because we are multiplying with a scalar, but when you are not multiplying with a scalar, the order must be preserved. Large object scalar arguments proceeding in a similar fashion. For alpha, t is a scalar and u and v are vectors, s and t are tensors, all being functions of a scalar variable. The results in the following table hold as expected. The simple rule, when obeyed, allows us to gain proficiency and transfer the scalar function in the scalar argument knowledge to tensors. Don't be fooled by the symbols. They are overloaded. If you already know how to do object-oriented programming, especially C++, you know what I mean by overloaded. That is, if I say 2 plus 3, the plus I'm using there is an arithmetic sum of 2 and 3. If I say Dupe plus Owosheni, the plus I'm using there is not an arithmetic. It's a concatenation to get the full name from the first name and the last name. That means that even though I'm using plus in those two expressions, the actual operation performed are different, and their operations are dictated by the context in which that plus exists. When an operation, when a symbol is used that way, you say that that symbol is overloaded. That is the meaning of overloading. That terminology comes from software, from programming. So don't be fooled by the symbols. They are overloaded. You are no longer in the real scalar space. You are in the Euclidean vector space, and the rules are slightly different. So all of this can be proved, and I think these are proved in the book. Most of them are proved there, but I don't want to go into detail. You can find out those things yourself. So if U is a vector and alpha is a scalar, and both of them are functions of t, you can do the product here. But the plus here is not the plus you are used to, because the plus here is adding three things, not just one, because the one on the left here has three components, and the one on the right also has three components. So the plus is adding the corresponding values to each other. And it is only appearing to be the same as the plus you are used to, but it is not. In this case, the plus is the same old plus, because on each side you have only one thing, because when you finish expanding this, you have only a single value. Also, you have only a single value here because it's a dot product. So you are adding two scalars together. So it is a scalar addition here. Here, it is a vector addition, so it is not the same. Here is a tensor addition. This plus is adding 9 things on the left and on the right. There are 9 quantities being added here, not 2, and not 1, and not 3, because the result of this expression is a tensor, and the result of this expression is also a tensor. Again here, the result, the plus here is overloaded because there are 9 things that are being added in this place. Here, what is happening here? Again, there are 9 things that are being added because the composition of 2 tensors gives us a tensor, and they have 9 components. So the plus here is adding those things together. Here, I want you to go to the chat room and tell me, is this plus sign here overloaded or is it not overloaded? Go to the chat room and tell me, this second to the last one, is the plus sign there overloaded or not? I'm going to the chat room to see your answer. Is the plus sign there overloaded or not? Is the plus sign overloaded? Are my students still there, or have they gone for the burial program? You will go to the burial program soon. Don't worry. I will release you at 11, so you can still have all the form of the burial. So I've seen 3 answers. I want more before I tell you whether they are correct or not. Ademola disagrees. Victoria disagrees. Khalid disagrees. Okay. Those of you who think it is not overloaded. Okay, those of you who think it's overloaded, tell me why. Those of you who think it's not overloaded, tell me why. Say it is overloaded because, it is not overloaded because. Tell me. That will show me that you know the meaning of overloading as I've explained. Emmanuel Adineko, I do not know. You see, when you do not know, I will give you 100%. Okay, so you do not know. You don't want to try, and you are telling me you do not know. Good. That's what I want. That's why I'm teaching this class, so that they will not know. Okay, go on. Any other person? If you said overloaded, why? If you said it's not overloaded, why? Did you just make a wild guess? When I have somebody who talks about overloaded, and somebody who doesn't, who talks it's not overloaded, then I will move on. I'm waiting. Don't waste the class time. Tell me something. Somebody talk. Somebody type something. Somebody. Help. Yes, Khalid. Khalid not only knows that the thing is not overloaded. Let me see. It knows that the reason why it's not overloaded is that the two things we are adding are scalars. So the plus is giving us the plus in the original meaning of plus, the arithmetic addition. So Khalid, kudos. So kudos to Khalid. So there's no overloading there, and it's because both terms give us scalars, so they are not overloaded. So the plus sign there is not overloaded. Okay, so let us see. We have one last term. It is overloaded in the last term because there are 9 things being added there. So the penultimate one is not overloaded, but the last one is overloaded. So we can go to page 21. So we're going to use some simple methods to differentiate some simple tensors, some tensors that have some properties that help us to be able to work with them easily. We have not yet gotten to the general method that will work with everything. We're just trying to say, okay, this tensor has some special characteristic. Therefore, why is the derivative of a variable identity tensor? If there is an identity tensor, okay, identity tensor is constant anyway. So why is it that the derivative of it is not a scalar 0, is not a vector 0, but a tensor 0, which is the annihilator tensor? I want to be sure that everybody knows why it is like this. So before I explain and go through this page, I want you to go to the chat room and tell me why is the IDT here this big 0. It's not the small 0 that is bold, and it's not the small 0 that is italic. It is the big 0. It is the IDT is the annihilator tensor, the 0 tensor. Why? Go to the chat room and tell me why. Why? Why is the derivative of the identity? I mean tensor, they are not JSON. Why is the derivative of the identity the annihilator tensor? Hi, chat. You are great. Yes, because when we differentiate the identity tensor, we are differentiating every time. When we differentiate the ones that are 0, it is 0. When we differentiate the ones that are 1, it is also 0. So there are 9 zeros packed in that same way. So they are all, there are 9 zeros, not just 1 0, not 3 zeros, but 9 zeros in a matrix pack. And that is the annihilator tensor. That is the reason. So let us therefore move on, because at least some people know what they are doing here. So we recognize the fact that the derivative of the tensor with respect to the scalar must give a tensor. The value here is the annihilated tensor of 0 tensor. This fact that the identity tensor does not change and has a 0 derivative leads to important results. We look at some of these as our first example. For example, you know that if we differentiate the equation S inverse times S is equal to I, that is the inverse of a tensor, even if it is a variable, multiplied by the tensor itself, is the identity. So if we differentiate this equation, what do we have? If we differentiate this equation, we have that this derivative is equal to the identity, and the derivative follows the rule of product, because composition is a product. The product rule applies to all products, whether they are scalars or they are vectors, they are tensors. The product rule is the product rule. The only thing you have to keep in mind when you are dealing with tensors is that you keep the order. You don't reverse any order, you don't change any order. As long as you are doing that, you are okay. So if that is the case, we have that if we transfer this to the other side, it becomes minus. So if we post multiply both sides by S inverse, they follow a important expression for the derivative of an inverse tensor with respect to a scalar parameter in terms of the derivative of the original tensor function. That is, ds inverse dt is minus S inverse ds dt S inverse. That is a very important result. And similarly, the s dt is minus S the S inverse dt. These two results are coming out of the fact that the product of two tensors, even if they are variable, when one is the inverse of the other, at whatever value of t, these are inverses of each other. So they are always multiplying together to give you the identity, which is a constant. So the fact that they are variable does not stop this equation, because when you differentiate the right-hand side, you get the annihilator tensor, which does not do anything when you add it. It's an additive. It's an additive. It is an additively neutral element. So that is what you get. So this is one result. We can see a relationship between the result, the derivative of a tensor with respect to time and with respect to t, a parameter, and we can relate it to the derivative of its inverse in these two equations. And this is where it comes from. So we can move on. Let us look at the constancy of the orthogonal tensor. In the case of the orthogonal tensor, it is not just the product of the tensor and its inverse, even the product of the tensor and its transpose, because the transpose of the orthogonal tensor, you remember, is the inverse. The transpose is the inverse. So what we did before, we now apply to the orthogonal tensor as the orthogonal tensor's inverse is its transpose. Its transpose is the inverse. So that means that if we differentiate QQT is equal to I, we have something that we had, something looking like what we had before, which is 0 here. But this one is a little bit different, because we can therefore write this. And if we write this, if you look at the expression on this line, you will see that what you have inside the bracket is the same thing as what you have on the left-hand side. That means that dq dt qt is the same thing as minus dq dt qt transpose. So the tensor omega is equal to dq dt q transpose is a negative of its own transpose. Therefore, it is q. If something is negative of its own transpose, it's q. That's the definition of q tensor. If something is equal to its own transpose, it is symmetric. If it is negative of its own transpose, it is q. So Any tensor that is negative of its own transpose, by definition, that is the definition of skew. You can go back and check. That's the definition of skew. So this, if there's a tensor we define like this, omega, that tensor is skew. And we are getting that from the fact that if you differentiate the identity, you are going to get the annihilator tensor. And let us use that information. That information has a physical application. Let us take a top. The top is like Okoto. Those of you who can speak Yoruba, I don't know what it is in Igbo. Okoto, you can be in any kind of shape. I just took a slice of it so that you can see what's going on inside of it. So let us say that originally the origin is at the tip of the top, where it's going to be rotating in 3 different directions. And then we can have a point P in it. When the torque is static, we say that point P is having a position vector of R0, which is a fixed point. But as soon as you give it a rotation RT, and remember, rotations and translations are rigid body motions. They apply equally to all locations in the body. So if you give a translation to a rigid body, you have given every point in the rigid body the same translation. If you give a rotation to a rigid body, you are giving every point in the rigid body the same rotation. We are about to draw a very, very important conclusion. The conclusion we are going to draw, let me tell you before we draw the conclusion. That conclusion is not obvious. The conclusion is that a rigid body has only one angular momentum. Every part of the body, has only one angular velocity. Every part of the rigid body has the same angular velocity. Remember that the distances from the origin are different, but the angular velocity at every point is the same. And we are going to prove that on the next page. Let us begin again. Let us state the parameters. One, you have a rigid body, for example, a spinning top. You say that a typical point P on it is R0. And then when you change it by a rotation that is time dependent, you get R, which is the tensor R operating on R0. That's what gives you this variable position vector. The variable position vector, it is a variable rotation operating on a constant position vector. Why? Because since it's a rotation you have given it, it's the same rotation that applies to every part of it, because rotation is a rigid body motion. We can find the velocity at this point by differentiating this position vector, because you know this is a function of time. If you differentiate on the left-hand side, on the right-hand side, what you have, the only thing that is varying with time is the tensor R, that rotation tensor, because the position vector of the original location is fixed. We know what location we were talking about initially. Now, if that is the case, you can say that R0 is R inverse R. Why? Why is this true? Why is this true? You can accept the first equality, but can you accept the second equality? If you can't accept the second equality, please go to the chat room to be sure you are awake to tell me why the second equality is correct. The first equality comes from differentiating this equation. What is this? Why are we replacing this? Why are we replacing R0 with R inverse R? Please tell me so in the chat room. Why is it correct to replace it with R inverse R? Why is it correct to replace R with R inverse R in that equation? Why is that C correct? Good. Good. Khalid, good. Aisha and Khalid are my hero. When we look at that, the rotation is an orthogonal tensor. Hence, instead of R inverse, we can write R transpose. Instead of R inverse, we can write R transpose. And if we write R transpose, we have arrived again at the omega we just finished defining. Because we defined an omega that's a skew tensor, and that is what we have here. It's a skew tensor. This omega, this quantity here is what we define as omega. Now, for every skew tensor, there's an axial vector such that if you give us any vector u, the skew tensor operating on u is written as that skew tensor, that axial tensor cross u. If you don't know, if you know why that is so, go to pages 16 and 17 in chapter 2 of the book, and you will see that that is there. But because some of you may be so lazy to go there, I have repeated what is in that on those pages 16 and 17 on the next slide. So because of that, we can say that V is omega cross R, where we define omega as the angular velocity of this top. And you can see that that is independent of any location. That is independent of any location, and that is the angular velocity, which shows that when a body is spinning, the angular velocity at every point in it is the same. It's a unique quantity to the body. So omega defined by this expression, the axial vector of the RDT, where R is the rotation, is called the angular velocity, and it is a unique function of any spinning body. So if you go to page 16 and 17 in chapter 2 of the book that I gave you, or that you can download from your site, from the site that I've directed you to, you see that if you have a vector u, you can always formulate the lambda, you can always formulate the omega tensor from it by just taking this ei alpha j. This one gives you 9 terms, and each term is a sum of 3 things. But that's not the problem. Our problem, given any vector, we can always create a tensor omega. It is the reverse. That is, given any tensor omega that is skew, can you always find u? Can you make u the subject of this formula? It's not obvious that you can do it. But to do it, just multiply both sides by eijk. If you multiply both sides by eijk, you go back again to the result we've always used, that eijk, ei alpha k. There's only one thing that is different here, k and alpha. So you can see that if you switch alpha and j, you have ij alpha, which gives you a minus, and then you see that it is delta k alpha. We have done that previously in the previous chapter. So that's UK. So you see that we can find components of the dual it's not dual vector. I think it's dual vector, but it's also called the axial vector, and it is half. You just have eijk. So given any axial vector, you can always find so what we are saying here is that if you know that omega is skew, then the big omega is a skew tensor, the small omega is the axial vector, and we call that the angular velocity. If this omega is this quantity, that's the angular velocity, and it's a property of any solid object that is in motion. That's a very useful information in continuum mechanics. Okay, so we go to the next example. Let's see how much time. Oh, time is gone. It's 11:55. I think, let me see. I think I can't go beyond. I think I should leave that. We start from page 27 next time. Let me not allow your head to explode. I think we've done enough introduction. Let me just go back and review what we were talking about. Let us go to the beginning. What we are talking about is that once you are trying to use calculus to do design, you are no longer dealing with simple equations of the jump type. I will bring some of those equations in next lecture so that you will see what the equations look like. They are relating tensors to vectors and scalars and so many things there. And there are derivatives with respect to the Euclidean vector space, which is a vector. You are differentiating with respect to a vector. You are not differentiating with respect to a scalar. And therefore, the methods of integral and differential calculus you know are not good enough. They are not strong enough to understand. And even when you go to a simulation package and they give you the result, you need to know the characteristic values of the tensors to be able to interpret the result. So even if you agree that somebody else is going to solve the problem for you because there's already a software embedded in your drawing tool that can solve the governing equations and give you the answers, can you interpret the answers? You cannot interpret the answers unless you know how to deal with tensors. That is why we spent a lot of time looking at the properties of tensors, and two properties we knew about tensor. A second order tensor has three principal invariants, and it has characteristic values, which are called the eigenvalues, and it has characteristic vectors, which are called the eigenvectors. Those are the critical things. If you don't know those things, or you don't know what those things mean, you don't know how to compute those things, you will not even be able to interpret your simulation results. So those who are asking me, why are we doing all these things? We are doing all these things to make you literate in the use of the simulation packages, at least. Even if you cannot do the finite element solutions. By the time you get to senior levels or postgraduate, when you are now confronted with doing the finite element analysis itself, you will need it even more. But that is the reason, and I'm just using this as a simple example. You can take any example from your simulation package, and that will be the reason why you are spending time on this. I think I should let you go. I don't want to take any of your time. I know today is supposed to be a time where we are burying the dead. So those of you who want to go and bury the dead, you are free to go. And I wish you a good week. We'll see you again next week. From next week, you are going to have tutorial classes, and Dr. Olayiwola is going to take a number of the questions from each chapter, and he will offer a face-to-face. There will be a face-to-face tutorial class. And please, I will advise Alma. No, it's not Alma. Who is the class rep? Please, the class rep here should liaise with me or Dr. Olayiwola, especially Dr. Olayiwola, so that you can set the correct time. And so if you cannot find a time outside the lecture hours, I will give up the lecture hours for the tutorial. But I am ready to teach so that you can quickly finish the term and you have a lot of freedom between the end of the term and the exam. That is the reason why I'm going on. But if you prefer to use the class time for the tutorial, be my guest. I will let you do it. But you agree with Dr. Olayiwola, who is the lecturer that is working on this course with me, and he will give you a face-to-face tutorial on that. For if you think you need it, fine. If you don't think you need, if you go to the book itself, and you can, all my examples are worked fully. So there is no, I don't give you any problem that I don't solve. So every problem is solved, and your exam is going to be within the scope of the solved problems in the book. We don't usually go outside that scope. So if you can do all of it, you will pass. No problem. Okay. So have a nice day. Goodbye. And admin, you can close the class.